All right. Okay, so where were we? We were looking at rocks. And so let's look at the rest of this. And so how is a rock different from a mineral? Well, rocks are made up of minerals. Minerals have to have a specific proportion, but rocks don't. So like granite doesn't have to have a certain amount of quartz and a certain amount of feldspar. Instead, you can have different amounts. So that's one difference. So rocks contain minerals, and those minerals don't have a specific proportion. Okay, and so we were talking about how sometimes there can be fossil impressions in shale. So here's a fern fossil inside the shale here, where it's been squished into the layers of mud. So, yes, so a leaf falls in the forest, falls into the mud. It could get preserved forever as a fossil, or the mud might get disturbed and wash downstream. But yes, if you leave your footprints in some mud, there's always a chance it will get preserved. So there have been human footprints found that are millions of years old, or at least precursors of humans. So that's always interesting to see. Dinosaur footprints. Okay, so chemical sedimentary rocks contain a lot of material that was once in solution. So like around here, we have a lot of calcium carbonate in our water supply. And that comes from all our limestone around here. And so what can happen is that can be precipitated. So the solution, crystals will start to form in the solution. So that's precipitation. Or sometimes there's biochemical origin. So there can be something involving life that brings these rocks into being. Okay, so they can be both of those. Okay, so some chemical sedimentary rocks. There's limestone, and that one is the most abundant chemical rock, and it's made, of course, from all these shells and things that remain because this was a shallow sea around here. And so there's a lot of that. Oceans have covered a large portion of land, and there's a lot of limestone. Microcrystalline quartz, and that has several different varieties called chert, flint, jasper, and agate. I don't want to make it full screen, Sean, because I want to be able to see messages. Otherwise, I wouldn't see that, but I can make it bigger. And get rid of that. Okay, all right. Anyway, so there are, so we'll be looking at those different types. Some are black, some are kind of greenish, some are a very ugly white. Anyway, but they're all microcrystalline, which means they have a lot of quartz in them, but instead of forming big quartz crystals, it's tiny little ones. So they don't show the clarity of quartz. Then there are evaporates, things where there was like salt water and it evaporated and leaves behind rock salt. And you can also get gypsum, which we've looked at some big gypsum crystals. And coal. Coal is compressed plant matter. And we're going to look at some peat later too, and which is compressed plants. Okay, but after they get fossilized, it can become coal. Okay, so sometimes the chert, which remember chert was one of the microcrystalline quartz things, so chert, all right, that can be found replacing materials. And so like the petrified wood, so petrified wood, you have the chert, the replacing the wood, so it gets into the wood cells, and then it crystallizes there. And so you end up with the chert replacing the actual wood. And but it still retains the pattern of the fossilized tree. And so anyway, so flint is usually black or gray. And jasper is usually red or yellow because it has iron in it. Flint has organic matter that makes it black. The petrified wood, you can also see the wood grain. And again, the silica, the church, the flints, the jaspers, the agates, microcrystalline silica. So they have a lot of silicon content, a lot of quartz. And agate, you often see concentric rings. So like a geode, you open it up, that's the agate that's in there. And so anyway, so there's a lot of those that can replace hollows, and you get your beautiful shapes out of that. So anyway, so chert is another way to refer to all these different kinds. So here's a beautiful agate, so a geode that you open up. And what there was solution in there, and then the solution evaporated slowly, and the crystals grew out from the sides. Now, some geodes are interesting. Take you over here. So this geode, let's get the camera here. Okay. Oh, that looks horrible. Anyway, it's not a very pretty geode. But what it is it's just got some quartz in there. And what they've done, though, is sometimes they'll call these dinosaur eggs. So let's see. And what they've done is played around with them so that they polished them around. So it's not naturally usually having this round shape around it. But what they've done is they have polished it so that then it looks like maybe it was a dinosaur egg that opened up and had some quartz. That one's not very good, but it was cheap. Okay, these are called septarian geodes. And so I've got a pair of them because it was split open. Let's get some light. And they're pretty cool. They look like they have a cool design in them of the different quartz and materials. What's interesting about these is that, well, why are they formed like this? They're found in mud, basically. And so where are they formed from? So they think what happens is that an animal dies. Okay, so it might be a fish or something, sinks down to the mud. And then what happens is that the fish is rotting over time, and this quartz comes in and replaces the fish. And so that's what you're ending up with. So this is the remnants of a dead fish, probably, or a mouse or something small. Anyway, so it's called a septarian geode. And so you find these rocks in the mud where other things haven't turned to fossils, but these have. Okay. And agate, of course, is a lovely thing. And of course, I have agate somewhere. But you've probably seen agate before. Here's some petrified wood. So this piece, you can actually see what looks like the bark of the wood there. And you can see it's got the red jasper color that's replaced the wood. So this is like a hunk of a tree branch or something. So anyway, so it's very cool. But yeah, you can still see the wood grain in the material. Okay, now chert doesn't necessarily look very attractive, So unfortunately, a lot of the samples are really kind of ugly looking. Um, so sometimes you just have this white, ugly rock, slightly tan colored. Okay, and but yes, that's your microcrystalline stone there. Okay, so anyway, so yeah, so they're not all attractive. Okay. All right, so you're going to be using, again, those sheets. Okay, so these are from pages from your book. And so what we're looking at now are these different forms of limestone and other chemical sedimentary rocks. And the limestones, the crystalline limestone, that's sort of what we were looking at. The chert is usually the light colored, the very quartzy material. And the limestone, of course, is mostly calcium carbonate. So you've got all of these are calcite, which is calcium carbonate. And so I don't have many samples of this because it's not something I usually collect. But we can look at fossiliferous limestone. So fossiliferous limestone is limestone where you can see the fossils. And of course, there is a lot of limestone around here. So I should go out in the yard and pick some up. Okay, so fossiliferous limestone. Here's a piece where you can still see the shell that are in there. Okay, so there's some shells here, and so fossils in the limestone itself. Okay, so yeah, so if you see actual fossils, that's called fossiliferous limestone. Okay, and okay, so let's go look at more pictures. Okay, so other biochemical rocks, so a lot of them are calcium carbonate. That's what makes the limestone. And so you'll often be able to find pieces of limestone that have fossils in them. And so it's pretty cool. Not all limestone seems to necessarily have fossils, but some does. And some around here does. And so usually you have to have warm water. And yes, Illinois used to be closer to the equator. So you don't want it too salty. And you want it to be, waves are pushing rocks around and stuff, breaking the shells up into small pieces. And it's oxygenated, which means it has oxygen that goes along with being shallow and clear water. So anyway, so those are things that can help build up a whole bunch of carbon or carbonate. Okay, so here's some fossiliferous limestone. This one has some nice, magnificent fossils there. Another one that can happen is coquina. Now, coquina happens when you've got a beach, like this one here, where the shells get beat upon by the waves a lot, and you end up with all these broken little shells. And so coquina has a lot of little broken shells, and they're all just mushed together, and you can still see the individual pieces. So the coquina, lots of little tiny pieces of shell. And so it doesn't have as much matrix, as much material in between as the fossiliferous limestone. It just looks like it's all shell. And this sample is not terribly good. And I believe the one in your lab isn't terribly good. But this is an excellent picture here. Okay. All right. Now, another cool material is chalk. And chalk is also made of tiny little shells. So I saw my piece of chalk. Okay, keep it wrapped up in a piece of plastic because it tends to drop pieces all over the place. Okay. So chalk is just white. And this chalk is from the Great White Cliffs in Dover. So it was collected there. And even under a magnifying glass, I did this the other day. It kind of worked. All right, let me move this picture. Okay, so I've got a magnifying glass over this. And you can start to see maybe the shells a little bit that make it up, but they're much too small for just a regular magnifying glass. But the cool thing about chalk, of course, is that you can write with it. And and yes, this is the same chalk that you would use in a blackboard, which people used to use. But nowadays, of course, we use whiteboards instead. No more chalk dust in the school, just lots and lots of pens that get thrown away. Okay, I'm trying to bring that the wrong way. Okay, so here's some, you may notice that this is the slate, only it's not slate, it's just the early stages of slate, so we'll talk about that later. So, but you can write on it with the chalk. Okay. Okay, now a lot of sedimentary rocks, of course, you have lithification going on. And so we talked about that already. The rocks, materials get compacted together and then they're cemented. And the three main materials, you might want to write these down, are calcite and silica and iron oxide, which is basically rust. So those are three of the materials that hold the detritus together. Okay, so calcite, silica, and iron oxide. And remember that those ions can move through the ground and then come out and fill up the pore space and lock the rocks in. So they crystallize in the pore spaces. Okay, so compaction, when you put pressure, then what happens is that particles line up if they can. And so then you've got compacted rock. So this is like particles of clay here. And here's showing some sand or gravel, and the mineral water comes through. So it's got these ions of calcium and silicon and things like that. And then they fill up the pore spaces and start forming crystals. So they cling to the rocks, and you end up with a rock that was just a loose set of gravel. Okay, now some things that you expect to see when you see sedimentary rocks is usually the rocks, of course, are from seabed. So they're laying on top of each other. Layers of material filtered down to the bottom of the ocean or the lake. And so you expect to see layers piled one atop another. And so, so these are also called bedding planes, and they separate the strata. So the strata are the beds, and then you'll have planes that separate. So you have other materials separating the strata, and you'll often see fossils. Fossils are really important because that allows us to date the the strata. And so we can look back in history, looking at these fossils. That really helps. So we're going to learn more about that in chapter 10, about how we date things using fossils. Okay. Oh, sorry. Okay. And like I was saying, if you drop a leaf in the mud, it might stay there forever. Here are raindrops even will sometimes have hit mud. And then if another loose sediment falls on top, so some more mud filters in, then what can happen is that it settles in the raindrop patterns. And then over time, it becomes fossilized. So you can actually have layers with raindrops, footsteps, and leaf impressions. Raindrops are cool. That indicated that the mud was perhaps up, so maybe the tide was down or the water level was down. So then there were raindrops, and then the water level probably rose, and then more silt covered up the raindrop pattern. Okay, now coal is also an organic rock. And so there are a number of different kinds. Bituminous coal is a sedimentary rock. And what happens is that you've got vegetation that falls down into freshwater or marine environments. But usually you have tropical wetlands. Okay, so yes, Illinois has a lot of coal because southern Illinois actually was a tropical wetland. We had an ocean that came up and to southern Illinois. So there was a branch of the ocean that came up that far. And so what you had was a lot of wetlands, and then the plants fall in the wetlands. And then what happens is if they go down deep enough, often there's no oxygen. And so instead of rotting, the plants eventually get compressed and turn into coal. So this is what Illinois used to look like. So a wetlands, tropical wetlands. Okay, so when you have a lot of vegetation that falls in the pond or the inlet, what you get is what's called peat. So where did I put my peat? So peat is just lightly compressed, so you can still see the plant material. And I had it the other day. Got way too many rocks. Oh, here's a good fossiliferous limestone. Thought I had some other ones. Here, you can look at this magnificent piece while I try to find my piece. Okay, and so this black thing here is a bit of a trilobite. And then we got a lot of shell fragments, so that's a very nice piece of limestone. And here's another piece that's been smoothed by waves. So can't really, so it's very smooth. So it's been in a stream or something. Anyway, it's kind of cool. You can still see the fossils, but they've all been worn down and smooth. Okay, peat, where'd you go? No, that's not the peat. That is a fossil, though. I hadn't opened up this box in a while. Okay. It's like, oh, there's some more of the rocks. Here's a little geode. Coal. Come on, Pete. Put everything neatly away in bags. And some things are in boxes. Hard to keep control of rocks. Okay, I'm not sure where my peat went to, so I will find it later. Meanwhile, let's look at some coal. So this is the bituminous coal. And later we're going to talk about the anthracite coal. And they're hard to tell apart. Sometimes one is shinier than the other, which actually, this one looks shinier than this one. Anyway, so they're different stages of coal. And so you start out with peat, which is compressed plant material. They burn it in Ireland for heat. And then it gradually gets compressed more and more. And you end up with coal. Sorry if you can't hear me. Still looking for peat. Okay, no peat. All right. So anyway, it's always fun in class for students to actually handle the peat. Since you can't handle it, I guess it's not quite as fun anyway. But here are the stages. So you start out with peat, which is this compressed plant material. You can still see the stems of plants in there. So it's compressed, but it's not unrecognizable. And then it starts to get compressed and becomes lignite coal, which is a soft brown coal. And then it gets more compacted and becomes bituminous coal. And then finally, it can get metamorphized under heat and pressure and become anthracite coal, which is hard black coal. Okay, so those are the various stages of coal. And we'll be looking a little bit more at coal later when we're talking about things that humans use. Okay, now one of the other fossilized materials that is one of my favorite are stromatolites. And stromatolites are these things. These are living stromatolites. They don't look like they're alive, but they are. These boulders are the stromatolites. This is in Shark Bay in Australia, which is one of the few places where stromatolites still live. But stromatolites used to be the dominant life form on Earth. In fact, they're the thing that is responsible for our oxygen atmosphere in a great deal. What they are is mats of blue-green algae and bacteria, and they build these rocks by their waste products. So like a fossil, I'm sorry, like a clam or an oyster puts layers of material around a speck, to build up a pearl. What happens is they filter water, and the stuff they don't want goes underneath them, and gradually it gets bigger and bigger. So all of these boulders have these mats of material on them, this algae, and the mats of algae are what built the stromatolites. And the fun thing about stromatolites is that they have been around since very early times. So they're often, 2-3 billion years old, and because they help produce the oxygen. And so stromatolites also are one of the things I like to collect. Again, reasonably priced, but also very interesting. They come in lots of different colors. And so depending on what materials they became fossilized with and absorbed. So here's a green one. Yep. And what you're looking at there are the layers of the boulder that was produced under the stromatolite. And then this one is a brilliant red. It has a lot of iron in it. And that one's from Minnesota. And they do have spectacularly old ages. So this one is about 1.8 billion years old. Oh, wait, it's backwards to me, but anyway. So that comes from the Mary Ellen mine in Minnesota. And this one is several billion years. That was the Cambrian, which is a long time ago. Okay, so when we get to the ages. And my oldest one is probably this little one, where it's actually had metal ore has replaced, so it's shiny with metal ore. And so it's got iron in it. And that one is 3.7 to 3.8 billion years old. And that one comes from Greenland. So anyway, so it's amazing that, remember, the Earth itself is only a little over 4 billion years. And these were some of the earliest life. And they used to be huge. They sometimes were 10 feet across. And they were the dominant life form on the Earth and made oxygen because of the blue-green algae. So say thank you to the stromatolites for your oxygen atmosphere. Okay, so very cool things to collect. The stromatolites. Okay. So again, sedimentary rocks usually come in layers called strata or beds. And they continue for a long distance because they're as large as the ocean, or at least that portion of the ocean, and or a lake. And they're similar in composition, color, and texture sometimes. And then you'll get some in that have new materials. So what happens is that you'll have new layers in where maybe a different mountain is eroding nearby, and that will give it different colors and different materials. Okay, so something like this is the Grand Canyon, and it's showing some of the strata here. And sometimes the stratas that are a series of beds, and if it's unique, then they get their own name. So like there's the Hermit Shale. It's a series of shale here along here, or the Coquino Sandstone. All these layers are a sandstone, and they're similar enough that they get grouped together. And then there's some limestone up here. So what was happening was the water conditions were changing, the depth may have been changing, the mountains nearby that were eroding to provide the material changed, and so you get different layers. And here you can see how these sedimentary beds have been disturbed. And so you can see how the earth faults have thrust upwards and broken the beds apart. But you can see like this bright red stripe following along here. Those used to be all lined up with each other, and now they've been tilted, and they've also been interrupted and thrust up at different levels. So that's Capitol Reef in Utah. Okay, so what's metamorphism? Metamorphism is where you are taking rocks and you are squeezing them and applying heat and pressure to change the appearance. So they can start as igneous rocks or sedimentary rocks or other metamorphic rocks. And so metamorphic, meta means change, morph means form or shape. Okay, pulling out some rocks here. These are rocks. Oh, okay. I just found more samples of my braccia and my coquina. Yep. I meant to get all the rocks laid out during my break, but I didn't get to. So going back to sedimentary rocks, this, of course, would be conglomerate, right? Look at the rounded pebbles. So that would be a conglomerate. You've got rounded pebbles there that are joined together. Here's a good sample of the breccia, because you can see the more broken, sharp-edged pieces that aren't as rounded. Somebody did draw a happy face on it, though. Some of those are more, a little smooth. Here's another piece showing the angular pieces. And the camera should adjust. There we go. So again, little broken pieces. So that's the breccia, right, for broken. And here's a better sample of the coquina. So the coquina, the stuff with lots of little seashells just jammed together. And you can see that one. You can easily see all the pieces of broken shell there. Okay, all right. So yes, I meant to do this during break, and instead I was writing a Google Doc for my other students. Okay. I'm not on video? No, I'm not on video, the person. Hopefully you're still seeing the rocks. Okay. Oops, no, don't want that. Okay, so metamorphic. And so it's changed from an original parent form. And so, so metamorphism can happen because of extreme temperatures and pressures. It can be low grade, where you can still sort of recognize the original material, the original rock that it came from, or high grade. And for high grade, it's very difficult to tell what rock it came from. So it doesn't have any original features. It certainly wouldn't have any fossils that were recognizable. They would be squashed mostly. Okay, though marble still has fossils in it sometimes. Okay, and slate can still have fossils recognizably in there. So it's not quite, but some of the other features aren't there anymore. All right, so let's go look at some of those. And again, you'll want to have your guide up perhaps. So the Metamorphic guide is this one. So let me go grab that. And remember, those are in the test 1 review area. Okay, so I'm going to leave that up so we can look at it, because these can be pretty confusing sometimes. Okay, so let's go back. All right. That stays big. Okay, so so we were here. Okay, low grade, high grade metamorphism. So shale can become slate. And so it's a low grade metamorphism. Slate still has layers. And so it's not that different. So this was the shale. We were writing on it a minute ago. Okay, so layers of materials. And for slate, you have it's hard to tell the layers in the slate, and I don't have too many samples here. But the slate, okay, you can't really see the layers very distinctly in here. They're still there, but they're compacted much more, whereas you can easily see the layers here, and you can break them apart. It's very fragile material, the shale, but the slate is much harder. And of course, slate is what school children used to use, and they would write on it with their chalk. Okay, and so that's a low-grade metamorphism. And a higher grade metamorphism would be when you have something like that becomes gneiss, which is one of the rocks we're going to talk about. So the original rock was granodiorite, granodiorite. And what happens is that the grains in there get lined up under strong forces, compressional forces. So here the grains are in random directions. And then under pressure, those grains line up, and it gives you this stripy appearance. That stripy appearance is indicative of a metamorphic rock often. Okay, other rocks don't usually have that stripiness in a single rock. So if you see a stripy rock, it's probably a metamorphic rock. Okay, so what occurs? What processes happen? Well, there's heat, there's pressure, and they're chemically active fluids also. So these can occur especially near a volcano where you have some magma coming up and it heats up the area around it. And so that's called contact metamorphism, and we'll be looking at that in a minute. But the idea is there's a lot of pressure often. The ground is being pushed by the magma as the magma comes up from below, so it's putting pressure on. Mountains are being built, and that causes pressure on rocks. And you've got all the heat coming off of the magma. So the magma doesn't actually have to touch it. It just has to be close enough that it provides heat. And then you can also have fluids moving through the rocks. And what happens is that those hot fluids can make the rock recrystallize by taking ions away and moving new ions in. So your calcium might leave and iron comes in. So ion migration is the idea that minerals or elements might move. Okay, so ions of elements. Okay, so they can get carried away and replaced. Okay, so where does metamorphism occur? Well, there's contact metamorphism. That's what I was saying. And that means that it doesn't have to be touched by the magma. It just has to be close to it. So near a body of magma, and the temperature increases. So that's called contact, or it's called thermal metamorphism. Now, regional metamorphism can occur across a whole region as there's a lot of mountains occurring. So think about the Alps. Those high mountains are occurring because Africa is pushing into Europe, or over in Asia. We've got the highest mountains in the world, the Himalayas, because you have India pushing into Asia there. And so mountains can be built under great pressure. Even without volcanoes, you get a lot of pressure and temperatures. So that produces huge amounts of metamorphic rock. And so I said already that Italy has a lot of marble because Italy is in the middle of that collision between Africa and Europe. Okay, so what's confining pressure? Confining pressure is the idea that there's pressure on the rocks. So there's rocks pushing down from below, from above, rocks from below pushing upwards. You've got from the side. Now, if it's confining pressure where you have equal pressure on all sides, then it doesn't deform the rock. Okay, so you don't get deformation. But sometimes you have pressure that is differential. Differential means it's different on different sides. And so if you have differential pressure, then that squeezes it and it warps. So here you can see this piece is undeformed, but once you start pressing harder on two sides, then it would possibly warp. Okay, it gets squeezed together, and that causes it to lengthen up and down, and so you get these wiggly layers. Okay, so underneath mountain chains, you'll often get this. So this is two colliding plates, perhaps. So like Africa pushing into Europe, and that's why you get the high mountains. So you get the Himalayas, you get the Alps, and the highest mountains are built from a collision of plates like that. Here in North America, we don't have mountains built that way currently. Most of ours are more volcanic. But we had mountains like that. The Adirondack mountain chain, which is along the East Coast, used to be the highest mountains in the world. But that was so many billions of years ago that they've been eroded down. Okay, so some of the features of metamorphic rocks, they have a foliated texture. And that's because the minerals get compressed. And what foliated mean is it's like folio, like a book. That's what it's supposed to be referring to. So layers on top of each other. Now, and so let's see, should I go to the next slide? Yeah. Okay, so this would be foliation. And so the minerals, you get pressure on two sides, the minerals start to line up, and that's what gives you your stripes. So they line up and they align with each other, and under differential stress, you get those stripy look. So foliation, stripy. Okay, now what else can happen is you can get non-foliated, and in that case, it's still under pressure, but what happens is that it recrystallizes sometimes, and you just get another coarse-grained looking rock. Okay, so what happens here is if the pressure's on all sides, that confining pressure, the crystals just get larger. They recrystallize often, but they don't line up in stripes. Okay, so let's look at the different kinds of rocks. So we already were looking at slate. And so slate comes from shale. So shale is the parent rock. And so when you're looking at rocks, what they do is one of the things they talk about is the parent rock. So for slate, the parent rock is shale or mudstone or siltstone. And so what happens is that it's in flat slabs, okay, slaty cleavage. So you've got here showing the texture of it, which shows that it has slabs. Now schist is something that has a lot of foliation, and it's very platy. So when you rub your finger on schist, you can feel it. It feels like scales or something. And what happens is this has a lot of mica, so it's very shiny. Okay, and it also is made from shale, mudstone, or siltstone. Okay, so let me find my schist, which is, of course, a fun word. Also, I had schist a minute ago. Quartzite. Okay, let's take a break while I find my schist. Okay, so here's a piece of it. Very sparkly. Okay, let's take a break while I get my rocks sorted out. Okay. All right. Okay, sparkly, scaly schist. Okay, take a break, and we'll be back to work on the labs, finish up this metamorphic chapter. Okay, I'm back. Okay, and so as you can see, this is the schist, and so I found a nice shiny piece, very shiny, and when you rub your finger on it, it's what's called platy, too. Those are like little scales, like they might be on a snake a bit. So they have a little bit of a platy feeling sometimes. And so I've got some different varieties here, but you can see that shimmer on it. And what can also happen, and that's because of the mica, so the mica is on there. You can sometimes get some that have a garnet forming in them. So when we look at the rock samples later, here's a little one where they're, oops. So this is under the magnifying glass. And what you can see are those little dots there in there. Those are little garnets that are forming. And so, so that sometimes happens too. So that can be a clue for your lab later. I believe he shows you some of the samples that he has have the garnets. And so you can see this one has little garnets embedded all over it. Sometimes they give a little flash. Okay. And this one also has some garnets, but it's harder to see because it's so dark. But there are some garnets forming in it. So anyway, so that's the schist. Now, oops. Uh-oh. Now, marble is another rock. Schist away. Okay, and so here's some quartzite and some marble. And some marble, of course, is you're familiar with looking at, you know, counter tops and statues. So this is some of the beautiful white Carrara type marble like Michelangelo used in his statues. And so that is something in the Carrara part of Italy. They have this incredible mountain of this beautiful white quartz. This beautiful white marble. And so lots of statues built from that. And of course, countertops. They don't have to be white. Marble can come in many different colors. And so this is one of the pages in your book, and it shows you where those mines are. And so when you look at, oh, things disappeared. The marble, it's non-foliated, medium to coarse grain, relative soft. What is it made from? Limestone or dolostone. So limestone, like around here. If we had a volcano around here, some of our limestone would turn into marble. Okay, now quartzite is also non-foliated, so it doesn't have stripes. What happens is that that's made from quartz sandstone. So sandstone can get made into quartzite. And I have a lot of samples of quartzite here. And it can take on a lot of appearances because when we look at sandstone, of course, sandstone comes in a lot of colors. Oh, well, here's another red one. So this deep red is pretty common. Here's a piece that is speckled with a lot of white. Okay, so that's the quartz that you can see in there. So yes, you'll see veins of quartz running through. So this one has a lot of the quartz. But yeah, that deep red is pretty typical. That's the sandstone that's turned into the quartzite. Hold on. Somehow we skipped over the phyllite and the gneiss. Okay, because I was skipping down to the thing. Okay, so anyway, okay, we did slate and schist. Then we should have done gneiss. So you don't say the G, it's just said gneiss. This is a gneiss rock, and one reason is because it's very easy to identify because it has stripes. So gneiss is a gneiss rock. And so that one's pretty easy to identify because of the stripes in it. So here's another piece to look at. And you can see those very distinctive stripes where it's been under pressure. And what happens is that the minerals line up in rows. And again, so that's gneiss. So it's very distinctive stripes. And it's made from shale or granite or volcanic rocks. So when you look at a sample, often they'll be this pinky color, or they can just be black and white. But the pink color, again, that would be usually from the granite, where you would get that, the feldspar. So the potassium feldspar with that pink color still carrying through, even though the rock, the granite was squished so that the crystals lined up in rows. Okay, and another rock is schist. And schist has very scaly foliation. So when you run your finger along it, it has, I'm sorry, we already did schist. Phyllite. Phyllite is the one we haven't done. So phyllite especially has this wavy look, and it's almost silky. And it can be made from mudstone or siltstone. And I only have a very small sample of that because even the whole department doesn't have much. So I had to steal one tiny little piece to bring home. And the thing is, it's very shiny. Got a rippled surface, which you probably can't tell, really. But it's a interesting material. And so maybe looking from the side here, not really being able to see the ripples. Anyway, a little bit. So you won't be having to identify that. So that is not going to be on your test, but it is something that you might be identifying in the lab. Okay, so those are all the different metamorphic rocks. And so the next thing we look at is mineral resources. But let's see, it's 227. So let's do this quickly. Okay, so a lot of minerals occur because you've got hot water solutions that run through rocks. So this again is going to happen a lot in a place that is volcanic. So there's magma and hot springs, and you often get ore deposits that way. So cooling magma bodies often produce this. So Yellowstone Park is known for its geothermal pools, very hot pools, and it's known for the geysers. That's because it's still an active volcano, actually. So it doesn't necessarily have to be cooling. It can be a magma body that, like under Yellowstone, is increasing in size too. But usually by the time people come around to mine them, they've cooled off. Now, pegmatites are large crystals. And so the pegmatites, usually, this is showing a pegmatites here, they've been removed, but very, very large crystals used to be in these rocks here. And so there were pegmatites here, large crystals, and then they were mined. And that will also happen in a fluid-rich environment. So unusually large crystals. They don't have to be this big. Usually a pegmatite, you're talking about something that's about 5 centimeters. That would still be a very large crystal. Hey, Robert, could you grab a rock for me? Okay. In on the blue, that little blue side table with the plants, there's one of your grandfather's rocks, the flat one, not the other one. One with the fossils? Those are pegmatites, I think. Okay, so anyway, so large crystals. So, all right. So my husband's grandfather was a rock collector, so sometimes some of the rocks I show were his. Okay, unfortunately his data book was lost, so we aren't entirely sure what they are, so we have to kind of guess. Okay, but in here I believe these are pegmatites, very large crystals. So they are more than an inch in here. Okay, so all right. Okay, where was I? So anyway, so when you've got a hot magma body, then all sorts of things can go on. You get heating around it that makes contact metamorphism. So this gray part is showing where you might have rocks that are affected and get metamorphized. You also have veins that are carrying hot fluids up, and so those veins will eventually maybe fill with minerals. So here's some gold in with some quartz. So this was fluid that was carried up, and it carried deposits of gold with it. So often when people are mining, they will follow a vein. Okay, and so you might have some large pegmatites, okay, so growing too because of large amounts of solution. And you might have smaller hydrothermal dissemination. So around here in this gray area, again, they're just tiny little cracks that carry warm fluid through. So you would get deposits all over the place, but it's not as distinct as a vein. Okay, so every year, a person in the United States uses a lot of materials. And so around 12 tons, at least when I wrote this slide. And so all sorts of materials get used. So, you know, you've got a cell phone, of course, and that used some copper probably and other materials in it. And you crossed a bridge, so you need some stone and gravel for the cement. You want potholes to be filled, so you need to fill them with asphalt or concrete. So anyway, so there's salt to salt the roads. And so anyway, we use a lot of materials. You buy a new fry pan, there you go. You got some iron or some copper. Hopefully not some lead, but we still use lead in materials. So, so lead is still a possibility. And of course you use energy. And a lot of energy comes from fossil fuels. So petroleum, coal, and natural gas. So anyway, so you do use a lot of materials per year, even though it may not directly be benefiting you, but on average, this is how much people use. And so their building materials so in the main groups, you've got building materials and industrial materials. So chemicals that are used to make whatever it is you want. And so non-metallic minerals have non-metallic elements that are used a lot. And we use them for their physical or chemical properties. And so there's a lot out there that happens. We're not going to go over all this stuff, of course. Okay, so let's talk about coal. So these are the deposits of coal across the United States. And you can see that Southern Illinois has huge deposits of coal. And that's the red here. That's the bituminous coal. So I keep screwing that up today. Bituminous coal. And so remember that is considered a sedimentary rock more. Anthracite coal has been through pressure, and that we only have a few deposits of that in the United States. which is close to the Adirondack Mountains, because I said those were once pushed up to be as high as the Himalayas, but they have now worn down. But there's still some coal left there. Okay, so if people think about coal coming from places like Virginia, and yet, Illinois has huge amount. And you can also see that these burn with different amounts of heat energy per pound. So BTU is a British thermal unit. It's a unit of heat energy. And you can see that anthracite and bituminous coal burn the best. And then the lignite is much smaller, 7,000 as opposed to 12,000. Okay, so we use a lot of energy from oil and gas. And to make oil and gas, then usually that's marine plants or animals. And so they fall into a marine environment, so a saltwater environment. So they fall to the bottom of the sea, your dead fish, and it can turn into oil. And it can rot away and produce natural gas that gets trapped down below. So also let's talk about these things called oil traps. So oil traps are cool. Okay, so there are different kinds of oil traps, and it's a place where you can drill down and find oil. And what you have to have are two types of rock. You must have a reservoir rock, which is permeable, and that's where the oil and the gas are inside the rock. But the rock has holes in it, basically. It's porous, has holes, and it's permeable. It means the oil can pass through it. And so oil and gas and water can be in these rocks. And then you have to have a cap rock, which is impermeable. And that keeps it from escaping up to the surface. So two types of rock, porous and permeable and impermeable. So a porous rock might be something like sandstone. A cap rock would be something that's hard, that's not going to let it through. Okay, there are 4 types that you'll need to know for the test. Okay, but luckily you'll have access to your book. So 4 types are anticline, a fault trap, a salt dome, and a stratigraphic or pinch out trap. And so the anticline, so there are drawings which are all together. I need to separate them out. So anticline, fault trap, salt dome, stratigraphic. Okay, so what's going on here? You've got this permeable layer of rock, so maybe some sandstone, or maybe some oil shale. And what happens then, there's a cap rock, maybe some granite or something is over it. So it can't escape. And what happens is that the oil gets squeezed up in this rock. And usually there's water down below that pushes the oil up, because oil floats on water, right? So the oil gets pushed upwards. And then, so the oil gets pushed upwards, and then gas gets pushed above the oil because it's less dense than the oil. And so the water is trapping it down below, and the cap rock is trapping it up above. And so an anticline is an arched layer of reservoir rock. So anticline is an arch layer of rock. Okay, and so when you want to drill down, you hit the gas first maybe, and then you get into the oil, or you could drill down directly into the oil. And so a lot of times oil wells also release natural gas, and they didn't used to collect it. Now, of course, we would like them to collect natural gas, which is mostly methane, which when we talk about climate change, if you just release the gas, it's very destructive to the environment. Now, the other thing that can be, the top layer of gas might have helium. Helium, that's where we get it. So helium balloons, where do you get your helium from? Helium is less dense than natural gas. So the helium is usually at the very, very top. And so people used to just let the helium go because they didn't realize that there was this valuable material. But then after it was identified, then it's very precious. There isn't that much helium in the world. We have to get it from wells like this. Like it's produced by radioactivity, so it's produced down here and it leaks its way up until it gets trapped. Okay, so the fault trap is where there's a fault line, where the rocks have shifted. So this has a permeable piece here. So this permeable layer here is also here, but it shifted so that the permeable layer is now cut off by the cap rock. And so it's blocked one end. So you had a layer there that was slanting slightly. And now what happens is that the water again pushes the oil up above it. And the gas is up above the oil. And so now you can drill your oil well down and get your oil out. Okay, now another type of trap is called a salt dome. Salt that might have been laid down under, these layers of marine environment. There might have been a lot of salt that was formed when the land rose up and the ocean waters dried up. So you might have layers of salt. But what happens is they tend to start expanding and rise up. And so what we've got here is they have blocked a permeable layer. So the salt has moved into this permeable layer. And so it's blocked on two sides. And so again, you've got water pushing the oil up. The oil pushes the gas up. And it's trapped against the salt and underneath the cap rock. And you've got some on both sides. And then there's the stratigraphic trap. And what happens here is this is like the original seashore. And so the original rotten stuff that became your oil and your gas is perhaps trapped against these rocks that maybe used to be the granite coast or something. Anyway, so basically these are a natural, the old natural environment. And that's called a pinch out because it goes for a while and then it stops. Okay, so you don't have a big layer like you have, in many of these big layers that will may stretch further. These are very iffy, so they have to find them. And so anyway, so that's due to the coast. So anyway, so anticlines are arched. Fault traps, you have to have an earthquake fault that moves the layers. Salt domes, the salt dome pushes its way up and blocks the permeable layer. And then the stratigraphic is just old coastline remnants. Okay, so those are the 4 layers, and yeah, they'll be on the test because, it's so easy to say, is it an anticline or fault? It's 4 things. Anytime I see 4 things, I think multiple choice question. Okay, so that will be on there, but you'll have open book, so won't be a problem. Okay, so hydraulic fracking. So this is the last slide. The idea is with hydraulic fracking that you are cracking the shale. So there's a layer of shale which has some oil in it. But it's not as permeable as sandstone. So it doesn't flow easily. So it's stuck in here. And the thing is, what they do is they shatter the shale by pushing down nasty hot fluids which have chemicals to loosen up the oil, like detergent, basically. And it's nasty stuff that loosens up the oil and allows it to flow more freely. And so anyway, so you dig down, you shatter it by putting down huge amounts of this fluid. It breaks the shell up, and then you have another pipe that comes up the other way, and you're sucking up this oil. Okay, so this fluid comes down, and it's crucial to have this nasty fluid. So this is pretty bad for the environment, because what if somebody has a water well over here? Well, then some of these nasty fluids can get into the well. And because you've broken the rock, then what happens is that it leaks out, right? So it can leak out of the shell area. So anyway, so toxic chemicals can pollute water supplies, and because you're pushing on the earth till you break it, it also can cause earthquakes. When we get to earthquakes, one of the cool things is to look at Oklahoma. Oklahoma used to have basically no earthquakes. Now they have hundreds of earthquakes each year. They're usually very small, less than a 4. And the people did have to go to the oil companies and sue them to say, stop making these earthquakes. Because the oil companies had to learn to not apply so much pressure that they were causing earthquakes over a 4. So anyway, but people still, it's hard to even live with just 2s and 3s shaking around, even though most people won't feel a 2. But yeah, so anyway, so Oklahoma now has hundreds of small earthquakes per year. Okay, that's the end of the chapter. So, we're going to go look at the lab. So work on your homework for this, and let's go look at the lab for the rocks. Okay, and I think those are pegmatites. Okay, so grabbing the lab, let's see, where is it? Yes, I have been away. And let's not forget to take roll too. Okay, so how do you do the lab? So we were looking at the igneous rock identification. And let's see, what we need to do is find the lab. So don't forget, under content, okay, so I guess we'll do the sedimentary and metamorphic more next week. But let's look at the igneous rock identification one, because that one you should try and do this week. But again, like I said, you can, it's due Sunday, but you can still turn it in. Well, you can keep working on the quiz up through at least Wednesday. Okay, so when we go down to the labs, hold on, labs. Okay, so there's a document you're supposed to look at, of course. And this tells you how to identify the rock. So here's the definition of pegmatite. The crystal just has to be larger than 1 centimeter. Okay, and so anyway, so phaneretic and aphantic and porphyritic, these are some of the words that you've learned, some you haven't. Vesicular, vitreous, pyroclastic, these are words that you learned. I'm not sure we covered aphantic or phaneretic, but that's just referring to the crystal size. And we talked about felsic materials and mafic materials. And we talked about how they have a different color index, which it depends on how many of the dark materials. Remember, mafic materials are the dark materials. And so the magnesium and iron, whereas felsic, remember, meant feldspar and silicon. And so anyway, so this your lab has some nice definitions and stuff to remind you. Then remember, we learned the word intrusive and extrusive. Intrusive is cooling slowly in the depth, so you get large crystals, and remember that's called plutonic. Extrusive is cooling rapidly, that's volcanic. Okay, so the rock identification chart for the igneous rocks, you are looking at how dark it is. The darker it is, the more likely it is to be more mafic, right? And you also look at the crystal sizes, so coarse-grained or fine-grained. Okay, so this is like the chart that I showed you. So you'll want to have the chart of the igneous rocks next to you when you're doing this. And looks like I'll have to bring it up again. And like I said, those are in your test review area. Okay, igneous rocks. Okay, so you want to have this next to you when you're trying to do the lab, because it will pretty much give away the rocks that you're going to do. Okay, so but it basically is the same thing as this, but without pictures. Okay, so your procedure is you look at the texture of the rock, is it fine or coarse? Then you look at how dark it is, and then where that intersects. So what he's saying is, look at the darkness. Is it mafic? Is it coarse? Then it might be gabbro, right? Oops, there. And or is it very light colored, but it's fine grained? Then it might be rhyolite. Okay, so those are the instructions. He's saying just use the chart and trying to identify things. Or is the texture one of these? Is it porphyritic or vitreous or vesicular, like pumice, right? Or pyroclastic with fragments. Okay, so let's go look at some of the samples. All right, and also don't forget I did put up the list of clues. Okay, so you probably want to print that off to use. And here are your igneous rocks. So let's look at sample. Oh, that's the PDF document. Let's look at the first image. But it's got other images, right? So it's got a pegmatic variety too, which means big crystals. Okay. Well, what do you got here? It's got biggish crystals, so that helps. It's also very pale, isn't it? Definitely looks more felsic. So big crystals, felsic, it's probably something that can be made into countertops. Okay. And it's also slightly pinkish, right? That pinkish color could be coming from the feldspar, the potassium feldspar. So you've got white quartz, you've got black mica, probably, and some white mica, so shininess here, and you got this pinkness that could be coming from the feldspar. Okay, so that should help you figure out what it is. Okay, so you would look and say, okay, coarse-grained, very pale. Where do these intersect? Okay, so that should give you a big hint there. However, let's look at the other pictures. So he's got a second picture. Let's see if I can jump to it here. I can jump to it this way. Okay. Oh, but this isn't terribly helpful, but it is a pretty reddish color. And again, that pinkish color usually comes from the potassium feldspar. And you can see at least 3 different substances here. So we've got some mica, shining, and we've got some whitish pieces, and we've got some more reddish pieces. So it looks like at least 3 crystals, 3 different minerals. And what has 3 minerals? Wonder what has 3 or more minerals. Okay, so anyway, so yes, so definitely this one looks like it's in the granitic column. That beautiful pink. Okay, and so anyway, they have don't think there's anything in these PDF documents. It just says igneous sample 2. Okay, so yeah, don't bother usually opening those. It's just frustrating. Here's another sample. Okay, so this is sample 2. And the one on the right is pretty not typical of what we were showing you. But on the left, you can see that this is fine-grained, because you can hardly see the crystals. And it's kind of a pale pink color. It's very pale again. So again, you'll just want to look at your chart and see where they intersect. Okay, so pale, fine grained. Well, there you go. So you found probably it's rhyolite. Now this piece is so dark, so there's some darker colors in here. And the crystals, yeah, that looks like quartzite to me. Okay, so anyway, but yeah, this piece is more typical. This is very much like what is one of the samples I showed you. Not terribly pink though. All right, so that's sample 2. Okay, so that's what you're going to do is try doing this. And like I said, if you don't get finished this weekend, we can go over this on Monday. So sample 3. Okay. So this one, you might say, oh, this looks like granite again. But it isn't. It just seems to have 2 different kinds of rock or minerals in here. And this is, and the percentage of dark to white looks around 50% or more. So you'd want to say, okay, well, this looks darker, right? So it's in here. So 25 to 45%. So it's probably somewhere in there. It's speckledy looking. And so what might it be? Big crystals, probably in this column, and so on. Okay, so anyway, so you can see how this chart is going to be very useful. And so you're going to want to definitely keep this on hand and just look at the samples and see what they are. Okay, let's see. It's about 3 o'clock. And here's some more varieties. Oops, that's sample 3. That doesn't look right. Okay, I'm not sure I'm going to believe it. Oh, hold it. Am I into my stone igneous? That doesn't look right. Okay, I'm going to take that picture out. That doesn't look very helpful. Some of the pictures were mixed up. I think this is sandstone. Okay, so anyway, some of them got mixed up early on. Dr. Dave had put them in the wrong place. So it looks like that one escaped getting edited. Okay, so I am going to delete. Okay, so I've deleted that one because that's just confusing. It shouldn't be in igneous rocks. It should be in the metamorphic rocks or the sedimentary rocks. Okay, so it's probably sample 3 in sedimentary. Okay, and I've got a copy of it so I can replace it. Okay, so anyway, so you're just going to do the lab, which hopefully I did not just destroy the whole lab. Okay, good. Good. We still have lab 2. Okay, we still have lab 3. All right. Igneous rock samples. Okay, good. All right, did not destroy everything. Whew. Okay. Okay, so anyway, so just go through, try and figure them out. This one's pretty simple, and I did give you clues. So anyway, so you should be able to figure out the igneous rocks. Okay, so what we're going to do is I'm going to let you guys go out early. And so you've had a long, exhausting day of looking at rock samples. And so let's just take roll and leave. Okay, so wake up so you can give me your name. Okay, let's see if Jennifer's here. Oh, no, Jasmine. Sorry, Jasmine. Wrong glasses. The lab clue announcements. So, Erica, Jennifer, is that you? Saying you're here?
Jasmine, I'm here.
Oh, Jasmine, I'm sorry. So the lab clues are if you go to the announcements. So you guys know if you need to get back to announcements, you just go up and click underneath the name of the class, and that'll bring you back to the announcements page. And so here are the hints for this. Okay. Okay, so Jasmine is here. And then we've got Tatiana.
Here.
Okay, great.
Here.
And Taylor?
Hi, I'm here.
Okay, and Elin?
Here.
Great. Corey?
Here.
Good. And Melissa?
Here.
Fantastic. And we have another Courtney. Oh, we had Corey before. Courtney Fallon. Courtney? Courtney? Let me check, see if they're out there somewhere. Nope, no Courtney. Okay. Okay, and then we've got Leah.
Here.
And we've got Samantha.
Here.
Okay, great. Alan. It's really hard when people probably are falling asleep. Alan was probably here. Okay, so I'll put a question mark there. Okay, Sean.
I'm here.
Great. And Michelle. Michelle, are you here? Supposedly you were here. Okay, you get a question mark. How about Abigail?
Here.
Thank you. And we've got Stephanie. Stephanie, are you here today? Okay. How about Aiden? Aiden? Nope. And Maya?
Here.
Great. Shauna?
Here.
Good. And Andy?
Here.
Yeah, survived. And Wyatt?
Here.
How about JL? Dale? J, nope. Alexander?
Here.
There you go. And
Hi.
that's okay. Ariana?
Here.
Good. Talisha?
Here.
Thank you. And Erica?
Here.
Great. Okay, this is fantastic. And the last person is Kirsten. Any Kirstens out there? Nope. Okay. All right. So, guys, thanks for sticking around. Probably things will, if you hate rocks, this is not helping. But anyway, I'll see you guys next week. So try to get those things done, but they always have leeway. All right. And I will have office hours tomorrow at 11:30. So if you need to see me.
Say that again. When we were office hours, I might actually need to take advantage of that.
Okay, so they're at 11:30. So if you go to your Google, so there's one of the announcements gives the link, but also if you go to your Google Calendar, oops, not that one, your Google Calendar, you should see the office hours in there because I invited you all to office hours. So
Okay, perfect.
Thursdays at 11:30. Okay. All right. See you tomorrow then.
Thank you. Bye.
Okay.
Thank you.
Bye.
Thank you. Bye.
Oh, thank you.
Bye-bye.
Bye.
I just had a
Hello?
question. Oh,
Okay, yeah.
you can go first.
Oh,
You
All right. My internet like cut out, so I had to like
Oh,
call. I'm here. I'm
who
Alan.
are you? Your name doesn't show up. What?
Alan Franco.
Oh, Alan. Okay, all right.
All right. Thank you. Thank you.
Good, because you cut back then. Yeah, that's one of the problems. So usually I try to find out who's here. Okay.
No, it's fine. But see ya.
Okay. All right, thanks. Bye. Okay, there we go.
I was just wondering, like in the grade book, some of them were saying like dropped, and I was wondering, like, I thought that your worst grade gets dropped. So, like, how is it saying things are already dropped?
Well, there's a whole bunch of zeros because you don't have grades yet. So it says it's dropping it, and it just picks the ones that are first in the row usually. So so that's why it says it drops it. It drops some of the ones that were zero.
Okay, but like at the end of the semester, it's gonna drop like the worst one, right?
It'll
Not
drop the worst one, right? So when you get a grade in there, if you got 10 points, it's not going to drop that. It's just dropping it now because it's a zero. So it'll keep moving the dropped.
All around.
Yeah, it moves it around, so it's very confusing.
Okay,
Yeah.
and it automatically does that, so it's not like you manually do
No,
that.
Dr. Dave set that up, so I don't manually do it. It just automatically picks out the lowest grades. And it starts with the ones near the beginning. Whereas if it started with the ones at the end, people wouldn't be, worrying about it probably already. Yeah.
True. Okay, and then my other question was, for the chapter 1 homework, you said that was extra credit.
Yes.
And I wasn't able to submit it yet. Is it
okay.
too late to submit it now?
Yeah, the extra credit, you can usually drop it in the Dropbox, and I usually don't put really a date on it.
Okay, because it said I got a 0, but I thought it was extra credit, so I was kind of confused.
Oh, okay. That's because it's not, I give it points, but you don't want to say it's worth 3 points, and then you got 3 points because people who don't do it, then they would have a 0 there. So, so it's not been graded yet, and it should be under extra credit.
Okay.
So
I just know that grades. It said 0, but I didn't.
But I can give it more points. So I haven't graded it yet. So after I grade it, it will have points.
Okay.
Now
I will put it in the extra credit folder when I get it done.
Okay. All right. Yeah. So that's where it goes, and you should be able to do that. So.
All right. Thank you.
Okay. Sure. No problem.
Bye.
Bye.
Hey, Miss Mo, can you hear me?
Yep. How you doing, Andy?
Good, good. How are you?
All right.
All right. I hate to bring this up.
That's okay.
I'm having difficulties with the first lab.
Oh no. Okay. So let's go look at it.
It's not like I'm having trouble identifying anything, but it's more so like I can't see.
Ah. Well, I told you his pictures were horrible. So I warned you.
Well, regardless, I have tried to like I can identify the hardness and stuff like that, but I can't see it's really hard for me to see the streaks.
Oh, well, you shouldn't have to usually, but yeah, I can understand that. Okay, so so I can go through and tell you what the streaks are. If you want, we could do that. Or I work with you to identify the samples.
Huh?
What did you say? I'm sorry.
Oh no, I'm sorry. Great. I can't speak English now. What I was trying to say was I managed to identify a few. I think I managed to identify a few, but I haven't gotten to the rest of them because vision. My vision problems.
Okay, well, let's go look at them. So let's see.
Let me see what I actually have here. I have Galena as 15.
Okay, so Galena
as
is 15. That's right. Yep.
I think Pyrite is 16.
Yep, that's right, K2.
Hematite.
Hematite.
That's 17. I have that for 17.
That's correct. Yep, that's good too.
This is the one I'm really not sure about. Pyroxide?
The pyrox. Which number are you looking at?
I have that for 18, but I feel like it's wrong.
Yeah, it's the magnetite. So one of the clues you would have gotten if we could see that video is that magnet stuck to it.
I would not have seen that.
So I wish you just said it instead of making you watch it happen, because if you can't get the video to work, then you can't see it. But yeah, it's magnetite. Yeah, so it's very dark, so it's hard to tell it apart from the pyroxene.
Okay, on 20, not 20, sorry, 19. I have 19 as the one that starts with a K.
Kaolinite?
That.
No. So one problem is that you weren't able to play with these. Kaolinite is really, really soft. And 19 is a gemstone, really. It's a corundum. And the only way you can tell that is to look at the shape of the crystal, kind of.
Oh, great. I've got so many freaking vision problems. That's lovely.
So anyway, so yeah, it's a hard material and much harder than kaolinite. So
like, I am literally like pressing myself up against the computer just to freaking look at the minerals, and I can't like see anything. It's frustrating.
Yeah, I'm really sorry about that. Yeah, I need to put in better ones, but I just haven't had the time,
No, it's fine. Don't worry about it.
Well, no, it's not fine. I should have done it, over this summer or something, but I didn't get it done. And
no, it's fine.
it's always you're starting the classes out, and there's always a lot of stuff to do, and it's like, oh, this thing needs better samples. Okay, but I really should do it. So let's see. So let's go back to minerals. Okay, and to mineral. So let's look at 19. Nope, not 19. Yeah, 19. And so it has no streak. It's white. Okay. But this is showing the crystal shape a little bit in this picture. Can you see it? Probably not.
Which one? Because there's two minerals.
Right. Well, there's the same thing.
Right.
And the one on the right, you can almost count the facets in the sides, which is 1, 2, 3, 4, 5, 6. It looks like. And the other picture kind of shows 1, 2, 3, 4, 5, 6-ish also.
And whatever you're seeing, I am not, so I'm just going to take your word for it.
It's not really good. Yeah. So anyway, so it definitely has sides to it. And so that's one reason it's not kaolinite, which is really, really soft. But it is corundum, which is which one thing they talk about usually is the color of it is usually a reddish color. So the left sample has a reddish sort of color.
The left you said?
Red color, almost. It's purple, kind of purple.
No, that's like half purple, like half white.
Well, that's because it's got a reflection off it more.
Of course.
Probably, yeah, of course.
Only because I'm trying to actually
paler there. But let's see. Where's our? Where's my lab?
Only because I'm trying to complete this thing.
Yeah, you should complete it. Anyway, that one's corundum. So find it in your list. It should be on the last page, I believe.
Oh, found it.
Okay.
1 second here. Let me write this down, because when I take the lab quiz, I want to just at least have the names of everything.
Which I guess I should have asked people if they had this part done.
Well, I want to at least have the names, because I have the.
No. Yeah, you should have. I should have gone over, because I've gone over so many of these with people. I think, and of course they got the rest, but yeah, probably not. I tried to give hints for a lot of the hard ones, but this one is one of the hard ones because it's just the pictures aren't great and it's kind of an unusual thing.
For 20, I tried identifying it, and by tried, I mean couldn't get past picture.
Okay.
It looks like very yellowish. Like
Oh, it is very
yellowy
yellow.
whitish.
Yep. So what is bright yellow?
That's where I was trying. That's
And
what I'm
it
trying to find here.
It's very smelly. That would be one of its characteristics. Stinky and yellow.
It's like 15 and 16. I know that.
I thought you were saying 20.
No, yes, I am saying I'm comparing it to 15 and 16 because apparently the quote unquote different property is that it's like 15 and 16.
Oh, no. That's really what it says?
Well, I mean, it's something along those lines anyway. Here, you know what? No.
I'm going to have to go look. Yeah, okay, so let me go to 20.
I hope I'm wrong. Or it has like the same composition as 15 and 16?
No.
Of course.
So where'd you get that clue? That's one of the clues?
Hang on, let me look.
18, 19, 20.
20, okay,
distinctive property.
Take a guess. It's a constitutive minerals 15
Oh,
and 16.
it's a constituent of minerals 15 and 16. Okay. All right. And it's stinky and it's yellow. And so, yes, so if you looked up 15, yes, so galena and pyrite both do have it. And galena is lead sulfide, and pyrite is iron sulfide. So what's
so what you're saying is this thing has sulfur?
Yep, sulfur. Yep.
Okay, well, the only other thing that has sulfur in it is
and it is stinky, yes.
I mean, the only other thing that has sulfur in it, from what I'm looking anyway, is a gypsum, but I already have that.
Huh? No, it's just plain sulfur.
Oh, is it really? Is it really just?
Yeah, really that's it. Sulfur? It's just sulfur is a mineral.
Oh.
I know it seems too simple, but yeah.
Oh, you know what? I'm just gonna not question this anymore. Oh, good Lord. Well, if I have this much trouble with frickin' 20, why the hell not? Let me go through the rest.
So 21 and 22 are also just an element.
They're also is one like carbon?
Well, yep, one of them would be carbon in the form of graphite.
21, distinctive property. Let me.
It's not 21.
So it's bendable, so it's not No, 21's bendable.
Yep, it is bendable. That would be carbon's not very bendable. But they're let's look at the picture. So for 21, I'm not sure if he has a good picture, though, is one of the problems.
Yeah, that seems to be one of many problems.
Yeah. Well, we had lots of samples of this, but see what happened was the person who owned the samples. That's one of the problems with our department there, is that we had someone who had brought in a lot of his own samples and was letting people use them. So they didn't buy samples, and then that guy retired.
Of course.
And he sold a bunch of his samples. And this was one of the ones that just disappeared. And we're all like, oh no, where is it? Fortunately, he had given me a sample of it. So I have my own sample of it. But yeah, the other teachers are all like, hey, where'd all this stuff go? So 21, why does it say mineral property? Or crystal shape. Oh, well, I guess that could, okay, well, that's sort of the crystal. Okay, so when you look at 21, it's just this kind of beautiful, what color would you call that?
Give me 1 second here. Like a brownish, maybe like reddish.
If you saw a pan made out of this, what would you say it was?
If I saw a pan made out of this,
Pan or dish or something made of this beautiful reddish brown metal.
We have a pan like this. I'm not even joking. We have like a pan that's like this.
And what is it?
Hang on, give me a second to look because this thing's a pain in the freaking. This thing's a pain in the ass to navigate.
So, it's often used in wiring in houses and stuff.
Okay.
And people steal it out of houses because they make it into pipes. And then they steal them out of the wall so they can recycle them. So like empty houses have to be guarded so people don't steal their beautiful pipes made of.
Okay, so. I'm looking through this.
Through the list?
Yeah.
Okay, let me grab the list. Okay. No, not that one.
Pink or white? No, it's not potassium because I already have that one.
Not that one.
No, it's not calcite either.
I gotta look in labs. God, it's so confusing.
Oh, is it a muscovite?
No. Muscovite is mica. That's not a metal that you make into pipes. It's a brittle.
I just saw the color, honestly.
Okay, what do we call this color? You needed the crayon box with the 64 colors. It's copper. Copper colored.
Copper colored. That actually might help.
It should. I think I just gave it away there.
Watch me still not find it.
Okay.
Just watch. Watch.
Okay, here's the mineral ID lab. Okay. All right. So let's go down here. Okay. So on the first page, there is about 10th down or so. Well, not even 10th. 1, 2, 3, 4, 5, 6. 6 down is a material that is dendritic. Dendritic means that it has branching crystal habit, which you can see this sample has a branching habit. It's malleable. It tarnishes green. And it's a pale copper color.
It tarnishes green?
It does.
Okay, give me 1 second because now I think I... Alright, let's see if I can manage to find this in this never-ending list.
So table 1, number 6 down. So 6 down.
Mineral identification chart. You're looking at the mineral identification chart, right?
I'm looking at the mineral identification chart. So,
okay.
Oh, we're still recording. Shoot. We don't want that.